Here we consider the forces on an L-shaped member that is pin-connected to two bodies. If the L-shaped member is in equilibrium, and if all other forces acting on it are negligible, then we can model it as a two-force member. We know that the line of action of the two forces acting on the two-force member must pass through the centers of the holes. We do not know the actual senses of the forces. The forces could act towards each other, or the two forces could point away from each other. In either case, they are equal in magnitude and opposite in sense. For now, we will assume that the two forces point away from each other. The two forces represent the action of the attached bodies on the two-force member. Therefore, once we have assumed the senses of the forces on the two-force member, the forces on the respective connected bodies must be equal but opposite. We don't even need to draw the two-force member itself, but we must represent the forces exerted on the connected bodies in a way that reflects the known line of action of the forces, their equal magnitudes, and their opposite senses. As discussed earlier, the two-force body would also be in equilibrium if the two forces were assumed to act towards each other. In this case, the forces on the two connected bodies would act as shown. We don't know the correct senses in advance. In drawing the free body diagram, we choose whether the forces act towards or away from each other arbitrarily. When we later apply equilibrium to one of the bodies, if we determine F to be negative, then we know the forces act in senses opposite to those we had assumed. While a two-force body can be of any shape, very often it is straight. In the case of a straight two-force body, the forces act along the length of the body. For a straight two-force body, we sometimes say the body is under tension if the two forces act away from each other as shown here. If they act towards each other, we say the body is under compression.